In the late 1950s, on the cold tarmac of a British airfield, mechanics unbolted a de Havilland Goblin engine from a retiring vampire fighter for the last time. It was the quiet end of a machine that had just rewritten the rules of aviation. Barely a decade earlier, in 1943, this same engine design had powered the Gloucester Meteor prototype, and by 1945, it made the Vampire the first RAF fighter to exceed 500 miles per hour. It was a mechanical triumph, yet within 15 years, it was completely obsolete. The mechanics who had unlearned the heavy complication of piston engines to master this single, screaming, rotating assembly now watched their revolutionary power plant become a legacy relic. The paradox of the Goblin was not that it failed. It was so brilliantly successful at opening the jet age that it instantly forced the industry to build the aircraft that would replace it. But the real story of the Goblin is not only the story of an engine left behind, it is the story of how a single spinning turbine taught Britain to leave the piston age, and what happened when the physics of flight demanded even more. Every week we tell the stories of British engines, factories, machines, and industrial names that once taught the country what power sounded like and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a mechanical dead end in a British design office in the early 1940s. In the early 1940s, British aviation was trapped inside a physical dead end. The problem was not a lack of ambition, it was a crisis of mechanical friction. The Aero engine, an engine built for aircraft use, where power, weight, reliability, and certification matter differently from road vehicles, had reached the absolute limits of traditional engineering. British supremacy in the sky was built entirely on the piston engine, an engine that burns fuel inside its cylinders to create power. The Rolls-Royce Merlin and the Napier Sabre were magnificent machines, but they were also monuments to mechanical compromise. To make an aircraft fly faster, engineers had to add more cylinders, force more air into the intake, and increase displacement. The total volume swept by the pistons inside the cylinders. But this brute force approach had a ceiling. By 1941, the sheer friction generated by thousands of moving parts, hundreds of valves, heavy forged connecting rods, and massive crankshafts meant that a piston engine was consuming a massive percentage of its own power just to keep itself turning. Furthermore, the propellers they drove were hitting the sound barrier at their tips, turning rotational energy into useless, deafening shock waves rather than forward thrust. In British design offices, engineers stared at their blueprints and realized a brutal truth. They could not add more cylinders, and they could not spin a crankshaft any faster without the engine tearing itself apart. Britain did not just need a new engine. It needed an entirely new way to understand power. The answer began not in a massive state-run facility, but in the independent mind of Major Frank Halford. Halford was one of Britain's most brilliant engine designers, a man who operated his own consultancy and had a long, trusted relationship with the de Havilland Aircraft Company. While Frank Whittle is rightly remembered as the father of the British jet, Whittle's early engines were complex and developmental. In April 1941, Halford set out on a different, parallel path. He wanted to build a jet engine that was not just a scientific experiment, but a rugged, reliable production unit. He called his design the Halford H1. Halford's philosophy was defined by a ruthless pursuit of simplicity. He looked at the staggering complexity of a late-war piston engine and decided to eliminate almost all of it. Instead of thousands of parts moving in violently opposing directions, the Halford H1 would rely on a single rotating assembly. To achieve this, Halford based his design around a centrifugal compressor, a massive, spinning metal disc with vanes that flings incoming air outwards at immense speed to compress it before combustion. This highly compressed air was then forced into 16 individual combustion chambers, where it was mixed with fuel and ignited. The expanding exhaust gases blasted backwards, driving a turbine engine, an engine that uses spinning turbine stages in high-speed gas flow to produce power or thrust. The turbine's only job was to extract just enough energy from the exhaust to keep the compressor spinning, while the rest of the violent gas flow shot out the back to create forward thrust. In a machine shop, the shift in manufacturing culture was absolute. For decades, British foundries had perfected the art of casting intricate aluminium blocks and cylinder heads, the upper part of the engine that helps seal the cylinders and contains combustion passages. Suddenly, those skills were irrelevant. The H1 required entirely new metallurgical disciplines. Machinists had to learn how to balance a massive, single-sided aluminium impeller to microscopic tolerances, because at 10,000 revolutions per minute, an imbalance of a few grams would vibrate the entire aircraft to pieces. Mechanics who were accustomed to adjusting valve clearances and smelling high-octane aviation petrol now found themselves staring at a hollow steel tube that burned paraffin-based kerosene. By April 1942, the first prototype of the Halford H1 was bolted to a test stand. When it was fired up, it did not roar or rattle like a Merlin. It emitted a deafening, high-pitched scream that shattered the quiet of the British countryside. The initial tests were a revelation. Within 2 months, the H1 was producing 2,300 pounds of thrust, making it the most powerful jet engine in the world at the time. This sheer power caught the immediate attention of the Air Ministry, but de Havilland's own jet fighter, the aircraft that would eventually become the Vampire, was not yet ready. The engine, however, was too important to wait. In early 1943, the H1 was transported to an airfield and installed into the Gloucester Meteor F940 prototype. On the 5th of March 1943, with test pilot Michael Dawn at the controls, the Meteor surged down the runway and lifted into the sky. It was a flawless flight. The aircraft was not shaken by the vibration of pistons. It simply sliced through the air, pushed by an invisible, continuous column of heat. The H1 proved so reliable that a version of it was even shipped across the Atlantic to power the prototype of the Lockheed P-80 Shooting Star, inadvertently helping to launch the American jet age. De Havilland soon fully absorbed Halford's design firm, forming the de Havilland Engine Company, and the Halford H1 was officially renamed the de Havilland Goblin. The name was fitting. It was small, fierce, and entirely alien to the old world of British aviation. The breakthrough had been achieved. Halford had proven that a single rotating assembly could replace the mechanical thunder of the previous 4 decades. He had bypassed the limits of friction, eliminated the propeller, and given Britain an engine capable of unmatched simplicity and power. The metal was cast, the thrust was proven, and the engine was ready. Britain now had to build an aircraft that could actually survive what the Goblin was about to do. The engine had proven itself in the air, but an engine cannot fight a war on a test stand. It needed an airframe. De Havilland's answer was the DH-100 Vampire, an aircraft designed explicitly around the dimensions and the unique physical demands of the Goblin. Developed under conditions of extreme wartime secrecy, the Vampire was conceived to climb fast and hunt down the latest generation of German fighters. Yet by the time the production lines were truly ready and the Air Ministry had finalized its requirements, the war was over. The aircraft officially entered Royal Air Force service in the spring of 1946. It is one of the great paradoxes of British aviation history. An engine born from the sheer survival panic of the Second World War arrived just a few months too late to drop a single bomb or fire a single cannon in anger. Instead, the Goblin was handed an arguably more important task. It became the machine that taught Britain how to survive the Cold War. To understand why the Goblin was a breakthrough, one must look at how it dictated the shape of the aircraft around it. The Vampire looked unlike anything that had come before. It featured a short, egg-shaped central nacelle, partially constructed from balsa wood and plywood, a direct manufacturing inheritance from the de Havilland Mosquito, and a strange twin-boom tail. This layout was not a stylistic choice. It was an engineering necessity forced by the engine. In an early jet, a long exhaust pipe creates internal friction that bleeds away precious thrust. To keep the Goblin's exhaust pipe as short as physically possible, de Havilland engineers removed the traditional rear fuselage entirely. They placed the tail on twin booms, allowing the jet blast to exhaust directly into the open air, just behind the engine block, the main structure holding the internal combustion and turbine sections. In the hangars of RAF stations like Oldham, the arrival of the Goblin forced a complete cultural reset. For a generation, British mechanics had measured their skill by their ability to manage moving parts. A Rolls-Royce Merlin or a Napier Sabre required them to understand the mechanical symphony of overhead camshafts, dozens of valves, and the carburetor, a device that mixes fuel and air before the mixture enters the engine. They were accustomed to chasing oil leaks, adjusting ignition timing, and the distinct, sharp smell of high-octane aviation petrol. The Goblin swept all of this away. When a mechanic opened the cowlings of a Vampire, they did not find banks of cylinders. They found a stout, barrel-like machine dominated by its centrifugal compressor, a single massive rotating impeller that sucked in air, accelerated it outwards, and crushed it into the combustion chambers. There were no valves to adjust. There was no ignition timing to constantly tune, because once the engine was started, the fire in the combustion chambers was continuous. Instead of aviation spirit, the airbases began to smell of kerosene, a heavier, oilier fuel that was cheaper, less volatile, and entirely alien to the old piston culture. Maintenance schedules were completely rewritten. On a wartime airfield, changing a damaged liquid-cooled piston engine could take a skilled crew the better part of a day. Disconnecting complex coolant lines, heavy radiators, and intricate mechanical linkages. The Goblin, by contrast, could be unbolted and slid out the back of a Vampire in a matter of hours. It was a self-contained unit of power. But simplicity did not mean a lack of danger. The mechanics had to learn a new kind of mechanical respect. The Goblin spun at over 10,000 revolutions per minute. At that speed, the centrifugal forces were constantly trying to tear the metal apart. A mechanic no longer worried about a sticking valve. They worried about microscopic stress fractures in the turbine blades. The turbine engine, a machine that uses spinning turbine stages and high-speed gas flow to produce power or thrust, operated at temperatures that would melt conventional steel. If a mechanic left a stray spanner inside the intake, or if a stone was sucked off the tarmac, the compressor would ingest it, shattering the blades and instantly destroying the engine in a catastrophic explosion of metal. For the pilots, the breakthrough was equally profound. The Goblin produced a type of power that required an entirely new physical instinct. In a piston engine fighter, pushing the throttle forward delivered instant torque, the twisting force that immediately bit into the air via the propeller, pulling the aircraft forward. A jet engine did not behave like this. When a pilot in a Vampire opened the throttle, there was a terrifying lag. The centrifugal compressor took time to spool up, drawing in more air, burning more fuel, and slowly building the column of thrust. But once that thrust arrived, the experience was transcendent. There was no massive propeller blocking the view forward. There was no violent torque pulling the aircraft to one side on the runway. There was just a smooth, unrelenting push that carried the aircraft effortlessly past 500 miles per hour. When a squadron of Vampires scrambled, the sound was no longer the deep, chest-rattling thunder of the Battle of Britain. It was a high-pitched, tearing shriek that rattled the windows of the control tower and signaled that the rules of the sky had permanently changed. By the late 1940s, the Goblin had achieved something vital. It was robust, dependable, and relatively easy to manufacture. It allowed the Royal Air Force to transition entire squadrons away from propellers without suffering the catastrophic failure rates usually associated with experimental technology. The Goblin had proven that jet power was not just a dangerous scientific experiment, it was a reliable everyday tool. But in the Cold War aerospace race, everyday reliability was about to collide with the brutal demand for infinite speed. The late 1940s marked the moment that the Havilland Goblin ceased to be an experimental triumph and became the industrial heartbeat of the Royal Air Force. The Second World War had ended, but a new, colder conflict was freezing across Europe. The Air Ministry no longer needed just a handful of fast prototypes. It needed a shield. It needed thousands of jet engines, and it needed them to be as reliable as the piston engines they were replacing. To meet this demand, the de Havilland Engine Company transformed its manufacturing footprint. The center of this new jet empire was the factory at Leavesden, just outside Watford in Hertfordshire. During the war, Leavesden had been a shadow factory, turning out wooden mosquito bombers. Now it was stripped of its woodworking tools and retooled for the atomic age. The machining lines at Leavesden represented a fundamental shift in British engineering. Workers who had spent a decade drilling oil galleys into cast iron cylinder heads now had to master the art of the centrifugal compressor. The Goblin's massive single-sided impeller was forged from a solid billet of high-strength aluminum alloy. It had to be machined to exacting microscopic tolerances, carefully polished to prevent stress fractures, and perfectly balanced. At maximum speed, this single disc of metal would draw in over 60 pounds of air every second. If it was unbalanced by even a fraction of an ounce, the vibration would tear the engine off its mounts. In a Britain where an engine could decide whether a fighter intercepted a Cold War threat or fell behind the horizon, power was no longer the mechanical thunder of pistons and oil. It was the high-pitched scream of a centrifugal compressor ripping the sky apart. By 1946, the Goblin was rolling off the Leavesden assembly lines and heading straight to frontline squadrons. RAF Odiham in Hampshire became one of the first stations to fully convert, with No. 247 Squadron trading their Hawker Typhoons for de Havilland Vampires. The tarmac of the airfield changed permanently. The deep, guttural idling of V-12 engines was replaced by the sharp, explosive crack of the Goblin's starting sequence. Mechanics no longer swung propellers to prime an engine. Instead, they loaded a heavy Kaufman starter cartridge, a large explosive charge resembling a shotgun shell, into the side of the engine block. When fired, the expanding gases violently spun the turbine until it reached critical speed, fuel was injected, and the engine ignited with a deafening roar. As the production run expanded, so did the power. Major Frank Halford and his team continuously refined the internal architecture. The initial production engine, the Goblin the Frerne, had produced 2,700 pounds of thrust, but the design was so robust that it could be pushed further without compromising its structural integrity. By widening the combustion chambers and refining the shape of the turbine blades, the heavily stressed metal fins that extracted energy from the exhaust, the Goblin II achieved 3,100 pounds of thrust. Soon after, the Goblin III pushed that figure to 3,350 pounds. This steady accumulation of power allowed the Vampire to evolve from a simple interceptor into a heavily armed fighter bomber. It could carry rockets, bombs, and heavy cannons, yet the engine rarely faltered under the weight. The Goblin became famous across the Royal Air Force for its sheer durability. Unlike the early axial flow engines, a different type of jet engine that used rows of smaller, delicate compressor blades, the Goblin's massive centrifugal impeller could ingest a startling amount of debris, ice, or even birds without suffering catastrophic failure. For the mechanics in the hangars, the Goblin built a profound sense of mechanical trust. The overhaul interval, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards, steadily climbed. It required far less daily maintenance than any high-performance piston engine before it. The service manuals, previously filled with complex diagrams for valve timing and carburetor tuning, were replaced by straightforward procedures for inspecting fuel burners and checking turbine clearances. The Goblin was not just powering aircraft, it was powering a new British industrial habit. But the true scale of the de Havilland Engine Company's empire was not confined to the airfields of the home counties. The engine was about to prove that British jet technology could become a global currency. The Royal Air Force was only the beginning. As the Cold War deepened, Allied nations urgently needed to modernize their own military fleets. They looked to Britain, and they did not want an experimental, temperamental power plant. They wanted the proven durability of the Goblin. Sweden became the first major overseas customer, purchasing the Vampire to form its first jet fighter wing. Switzerland, Norway, France, and India soon followed. For these nations, the appeal of the Goblin was not just its top speed, it was its independence from complex infrastructure. A foreign air force could operate the Vampire from austere airfields without needing a massive, highly trained logistical tail. The centrifugal compressor was immensely forgiving. It could handle freezing Scandinavian winters, abrasive Indian dust, and rough runway debris with the same brutal reliability. De Havilland did not just export the completed engines, they exported the industrial blueprint. The Goblin was built under license in Sweden by Svenska Flygmotor and in Italy by Fiat, embedding British engine architecture into the very heart of European post-war recovery. By the time production peaked, over 3,000 Vampires had been constructed globally, requiring an immense continuous supply chain of spare parts, replacement turbines, and fresh impellers flowing outward from British factories. This mechanical reliability was publicly cemented in July 1948. a squadron of RAF Vampires powered by the Goblin 3 took off from Stornoway in Scotland and crossed the Atlantic Ocean to North America. It was the first time jet aircraft had ever completed the crossing. The engines ran flawlessly for hours over open water, a feat of sustained high RPM operation that would have been considered a suicidal gamble with early axial flow designs. The sheer success of the Goblin allowed the de Havilland Engine Company to scale the architecture. Major Halford knew that larger, heavier aircraft would soon demand thrust that the Goblin simply could not provide without becoming dangerously overstressed. The solution was the de Havilland Ghost. Introduced in the late 1940s, the Ghost was essentially a massive evolution of the Goblin's centrifugal layout. By increasing the diameter of the impeller and refining the internal airflow, the Ghost pushed power output to a staggering 5,000 pounds of thrust. This larger engine allowed de Havilland to power the next generation of British aviation. It was fitted to the de Havilland Venom, a much more aggressive fighter bomber that replaced the Vampire. And most famously, it powered the early versions of the de Havilland Comet, the world's first commercial jet airliner. For a brief shining period in the early 1950s, the de Havilland Engine Company was not just building fighter engines, it was powering the dawn of global civilian jet travel. This was the absolute peak of Halford's centrifugal empire. Across Britain, from the machining lines at Leavesden to the test cells at Hatfield, thousands of workers were employed in casting, polishing, and assembling the massive aluminium impellers. On military air bases from Hampshire to the Alps, and on civilian tarmacs across the empire, the air smelled of kerosene and rang with the high-pitched shriek of de Havilland turbines. The de Havilland Engine Company had built the machine that opened the jet age, but the very shape of that machine was hiding a physical limit that no amount of British engineering could engineer away. The collapse of a British engine empire rarely begins with a catastrophic mechanical failure on the runway. It usually begins quietly in a room full of paper when the physics of the future suddenly outgrow the metal of the present. For the de Havilland Goblin, the first small crack appeared not in a shattered turbine blade, but in an Air Ministry briefing room in the early 1950s. The Cold War was accelerating. Intelligence reports indicated that the Soviet Union was developing swept-wing aircraft capable of pushing toward the speed of sound. In response, the Royal Air Force issued urgent new requirements for a supersonic interceptor. British aircraft designers returned to their drawing boards, attempting to sketch a fuselage that could pierce the sound barrier. But every time they tried to design a supersonic fighter around a de Havilland engine, they hit a physical wall. The problem was the very component that had made the Goblin a masterpiece, the centrifugal compressor. Because it compressed air by violently flinging it outward to the edges of a massive spinning disc, the engine block was inherently fat. It was, effectively, a barrel. At 500 miles per hour, the aerodynamic penalty of this wide frontal area was entirely acceptable. But as an aircraft approaches Mach 1, the air in front of it compresses into a dense, solid shock wave. Pushing a wide barrel-shaped fuselage through that shock wave created a staggering amount of aerodynamic drag. The aircraft designers realized a brutal truth. They could not shave the fuselage down to a sleek, supersonic needle if they still had to wrap it around a massive de Havilland impeller. The Goblin was not broken. It was simply the wrong shape for the future. This physical limitation triggered a massive, systemic technological displacement. The British aviation industry began shifting its faith, its government funding, and its future toward an entirely different architecture, the axial flow engine. Instead of a single massive disc-flinging air outwards, an axial flow jet engine uses multiple rows of small, delicate spinning blades to compress the air by forcing it straight backwards in a continuous line. Because the air flowed straight through, an axial flow engine, like the new Rolls-Royce Aviation, could be built incredibly narrow. It was a spear, not a barrel. It allowed aircraft designers to build the sleek, swept-wing fighters the Cold War demanded, such as the Hawker Hunter and the English Electric Lightning. For the de Havilland Engine Company, this shift was a structural trap. Major Frank Halford and his engineers had spent a decade mastering the metallurgy, the machining, and the unique thermodynamics of centrifugal power. Their factories at Leavesden were perfectly calibrated to cast and polish massive single impellers. Their mechanics understood how to balance them. Their entire corporate identity was tied to the rugged, wide-bodied simplicity of engines like the Goblin and the Ghost. When the Air Ministry made it clear that the next generation of frontline combat aircraft would strictly require axial flow engines, de Havilland found themselves on the wrong side of the aerodynamic divide. They attempted to scale up their existing technology to meet the new power demands. But physics is unforgiving. Making a centrifugal engine more powerful meant making the impeller even larger, which made the engine even wider, which created even more drag. The very strength that had allowed the Goblin to define the early jet age, its simple, wide, robust, rotating assembly, had become a fatal liability. The orders from the Royal Air Force for new frontline centrifugal fighters began to slow. The de Havilland Venom, powered by the larger Ghost, was a highly capable aircraft, but it was fundamentally a stopgap, a final expression of a design philosophy that had reached its absolute limit. In the hangars, mechanics still trusted the Goblin, and export orders to foreign air forces still kept the machining lines at Leavesden busy, but the momentum had definitively shifted. The future of British military aviation was being written in Derby by Rolls-Royce and in Coventry by Armstrong Siddeley. The machining lines at Leavesden, once the loudest and most confident spaces in British aviation, began to face an uncertain horizon. The workers there knew how to build the Goblin better than anyone in the world. They had perfected the casting of the heavy outer casings and the meticulous balancing of the central shaft. But they could see the trade press praising the Rolls-Royce Avon. They could see the new narrow-bodied prototypes dominating the Farnborough Air Show. The massive capital investment required to completely retool Leavesden for axial flow production, to replace heavy lathes with precision blade forging equipment, was an economic mountain. De Havilland Engine Company tried to pivot. They began the agonizingly expensive process of developing their own massive axial flow engine, the Gyron, hoping to leapfrog the competition. But creating a completely new jet architecture from scratch in the middle of the Cold War was an endeavor that drained staggering amounts of cash. The engine that had opened the jet age was still running flawlessly across the globe, but the market around it had already decided to move on. Britain did not stop needing thrust. It stopped needing that shape of thrust. And in a ruthlessly competitive aerospace industry, losing the shape of the future meant losing the company itself. The attempt to survive the axial flow revolution broke the de Havilland Engine Company financially. Their massive new engine project, the Gyron, was intended to be a technological titan, but it was funded almost entirely out of the company's own reserves. In the ruthless economics of Cold War aerospace, an independent engine maker could not shoulder that level of research and development alone. They needed the government to commit to massive fleet orders to make the new tooling, the new foundries, and the new machining lines pay for themselves. But the political and military landscape of Britain was about to shift violently. In April 1957, the British government published a defense white paper that fundamentally altered the trajectory of the nation's aviation industry. Driven by cost-cutting and a belief in the supremacy of the guided missile, the government concluded that the era of the manned fighter aircraft was drawing to a close. Almost overnight, the Air Ministry canceled a swathe of supersonic aircraft projects. For de Havilland, the timing was catastrophic. The Gyron lost its intended airframes. The investment evaporated, leaving a massive financial hole in a company that had once dominated the skies. This policy shift triggered a devastating ripple effect across the British engine market. The government looked at a fractured industry of independent manufacturers, de Havilland, Bristol, Armstrong Siddeley, Napier, and realized the state could no longer afford to feed all of them. The directive was clear: merge or die. The state mandated corporate consolidation, the process where companies merge, acquire, or absorb other companies to survive on smaller, consolidated government budgets. Simultaneously, the vast global service network that had sustained the Goblin began to collapse. During the glory years, the sheer volume of vampires flying in Sweden, Switzerland, France, and India had required a continuous, highly profitable stream of spare parts. Leavesden had churned out replacement impellers, turbine blades, and combustion chambers by the thousands. But by the late 1950s, those foreign air forces were modernizing. They were buying sleek, swept-wing American jets or the newer British Hawker Hunters. The export orders for Goblin spares slowed to a trickle. The vast machining lines in Hertfordshire had to be scaled back. Parts scarcity, once unimaginable for such a ubiquitous engine, began to affect the remaining squadrons. Out on the airfields, the physical reality of the Goblin was also retreating. The Royal Air Force had long since moved the Vampire away from frontline interceptor duties, relegating it to advanced training roles. For the mechanics, the engine that had once represented the cutting edge of human speed was now just an aging, thirsty piece of legacy equipment. The fitters who had first learned to trust the smell of kerosene and the shriek of the centrifugal impeller were now senior technicians, teaching a new generation how to work on the complex, narrow axial flow machines. Compared to the new engines, the old Goblin was increasingly seen as loud, heavy, and primitive. The corporate death blow was inevitable. The de Havilland Engine Company, the fiercely independent firm that had pioneered the British jet age with a single rotating assembly, was told its independence was over. In 1961, the company was absorbed into Bristol Siddeley. The foundries at Leavesden, which had once cast the great aluminium blocks of the Goblin, were reorganized to serve a larger, more anonymous corporate structure. Major Frank Halford had passed away in 1955, and now the de Havilland badge itself began to fade from the engine blocks. The final bitter irony arrived in 1966. Rolls-Royce, the company whose sleek axial flow Avon had rendered the centrifugal compressor obsolete, purchased Bristol Siddeley entirely. The empire that had built the Goblin was swallowed whole by its greatest rival. When the final Vampires were retired from British service, there was no grand ceremony for the engines that had ushered in a new age. They were simply unbolted from the airframes in cold hangars. Some were sold to breakers' yards, their high-strength aluminium melted down for a fraction of its original worth. Others were pushed into the dark corners of storage depots, covered in heavy tarpaulins. Their service manuals, once highly classified documents, left to gather oil stains and dust on workshop shelves. The engine still ran. The thrust was no longer enough. The export orders vanished. The state withdrew its money. The airframes were scrapped. The factory lost its name. The sound faded from the airfields. The badge disappeared into a merger. The Britain it powered was gone. The Goblin had lost the sky. What remained was the task of figuring out what to do with the metal left behind. The de Havilland Engine Company ceased to exist as an independent entity, its name wiped from the ledgers of British aviation by the brutal economics of the Cold War. But the death of a corporate badge is never the true end of a machine's influence. Today, the de Havilland Goblin survives, scattered across Britain in a completely different form. If you walk into the de Havilland Aircraft Museum in London Colney, or wander through the vast, quiet hangars of the RAF Museum at Hendon or the Imperial War Museum Duxford, you will find them. They sit quietly on heavy steel engine stands, often displayed with their cowlings removed. To the modern casual observer, they look like relics of a primitive, clumsy era. Fat, wide barrels of aluminium and steel that clearly belonged to a time before the sleek, supersonic, swept-wing fighters took over the sky. Out in the private restoration world, the survival of the engine is even more physical. When foreign air forces, like the Swiss, finally retired their last Vampires decades later, a quiet migration occurred. Enthusiasts and specialist restoration shops in Britain bought the surplus airframes and shipped them back. Today, inside private British hangars and specialist aviation sheds, there are still mechanics who turn wrenches on original Goblin engines, keeping the old centrifugal technology alive for classic air shows. But this is not nostalgia. A preserved Goblin engine, whether sitting behind museum glass or spooling up on a private runway, is a physical argument about a very specific, dangerous moment in British industrial history. It represents the exact mechanical threshold where the country had to unlearn half a century of engineering habit. For the mechanics, the fitters and riggers who had spent their early careers covered in the oil of Rolls-Royce Merlins and Napier Sabres, the Goblin was the bridge between two entirely different worlds. It taught a massive British workforce how to stop thinking in terms of reciprocating mass. It forced them to stop worrying about snapped push rods, burnt exhaust valves, and cracked cast iron cylinder heads. Instead, it demanded that they respect the terrifying, invisible forces of high-speed rotation and extreme thermodynamic heat. It taught British foundries and machine shops that casting a solid block of iron was no longer enough. They had to master the microscopic tolerances of a massive centrifugal impeller. It taught the airfields of the home counties to stop smelling of highly volatile aviation spirit and to start smelling of heavy, oily kerosene. The old service manuals, the oil-stained books that once sat on workshop benches detailing complex ignition timing and carburetor tuning, were replaced. The new manuals demanded an understanding of turbine clearances, compressor balance, and single-shaft reliability. The Goblin forced a total rewrite of what British mechanical trust actually looked like on the ground. It remains one of the great paradoxes of British military manufacturing. The Halford H-1 was designed in a desperate, secretive rush to defend Britain from the Luftwaffe. Yet the production Goblin arrived just too late for the Second World War. But in missing that war, it achieved something arguably far more difficult. It made jet propulsion ordinary. Early axial flow jets, with their rows of delicate compressor blades, were fragile and temperamental, prone to compressor stalls and catastrophic failures if they ingested so much as a stray stone from the runway. The Goblin, by contrast, was an absolute brute. Its massive centrifugal compressor swallowed ice, runway debris, and thousands of hours of hard, unforgiving training flights. It proved to the Royal Air Force and to air forces across the globe that a jet engine did not have to be a suicidal experimental rocket. It could be trusted as a daily tool. The market forces of the late 1950s and 1960s eventually destroyed the environment the engine needed to survive. Aerodynamics demanded that engines become narrow spears rather than wide barrels, pushing the industry relentlessly toward the axial flow layout. Corporate consolidation demanded that independent manufacturers merge or die, leading to de Havilland's absorption into Bristol Siddeley, and finally into the massive monopoly of Rolls-Royce. Technological displacement and financial pressure rewrote the entire structure of the British aerospace industry. The centrifugal compressor could not cheat the physics of supersonic drag, and Major Frank Halford's fiercely independent engine firm could not cheat the consolidated balance sheet of the Cold War. But the machines outlived the balance sheets. The engineering survived the corporate mergers. The men who learned their trade bolting, goblins into the wooden fuselage vampires at Leavesden, carried that knowledge forward into the supersonic era, building the foundations of the modern aerospace network. The engine had done exactly what it was built to do. It had taken a country entirely dependent on the piston and forced it into the jet age. Somewhere in a British museum hangar, a de Havilland Goblin sits perfectly silent on an engine stand, its massive centrifugal impeller frozen under the lights, a solid block of early jet age metal still holding the memory of the first time British mechanics truly heard the future. Subscribe to the channel for more stories of the machines that built Britain. See you in the next video.